So, have you ever come across something called IS 4081? I mean, it sounds like it could be a secret weapon or maybe a classified mission file, right? And in a way, it does deal with something pretty powerful, controlled explosions. But the real story here, the real secret, isn't what's in the document. It's the incredible story of how we can even read it in the first place. Let's dig in.
Okay, so here it is in all its official glory. IS 4081 is the safety code for blasting and related drilling operations. Basically, it's the rulebook, the manual for anyone who handles explosives in construction or engineering. And as you can imagine, it's a super important document designed to keep people safe.
And this isn't just some internal company memo. No way. This code was published way back in 1986 by the Bureau of Indian Standards, also known as BIS. That is the official national standards body for all of India. So yeah, this is a serious government-backed safety standard that's been on the books for decades. And if you look at where it came from, you really get a sense of its importance. It's from the Civil Engineering Division, and even more specifically, the Section for Construction Management and Safety. This just tells you this is a highly specialized document, written by the experts for the experts. Okay, so you're probably thinking the next logical step is for us to just break down what's inside, right? Go through all the safety procedures for drilling and blasting. And yeah, it's a fascinating, pretty high-stakes topic for sure.
But we're actually not going to do that. Because as important as the rules and regulations inside this document are, believe it or not, they aren't the most interesting part of its story.
The real story here, the secret we're really diving into, is why. Why is a super technical official government safety code from 1986 available for anyone, anywhere in the world to just download and read completely for free right now? It's a story all about access to information.
You know, making this happen takes a whole chain of events, kind of like an ecosystem. First, you have the creator, the Bureau of Indian Standards, that writes the code. Then you have a contributor, in this case a nonprofit called public.resource.org, that steps up to digitize it. And finally, you need a platformer, like the Internet Archive, to host it and make it permanently available for everyone.
And this whole effort isn't just about making things convenient. It's actually driven by a really powerful philosophy. This quote right here gets to the absolute heart of it. It is the right of all humans to know and speak the laws that govern them. And when you think about it, safety codes and standards, well, they're a form of law, aren't they? They govern how we all work and live safely. The whole idea is that this knowledge just shouldn't be locked away.
And this isn't just a nice idea. It actually has serious legal muscle behind it. The document is made available because of India's landmark Right to Information Act of 2005. This law basically empowers citizens by giving them access to information that public authorities control. It turns a noble idea into a right you can actually use.
And the goals behind this idea of open access, they are huge. I mean, it's not just about one document. It's about promoting education, ensuring public safety, providing equal justice, creating a better informed population, even fostering world trade and peace. The core belief here is that open access to knowledge is a fundamental piece of building a better world.
So that's the why. We get it. But now let's peek behind the curtain and look at the how. I mean, how exactly do you take a document like this and preserve it and share it in a way that actually lasts and is accessible to literally everyone?
Well, this timeline really shows you what a long journey it's been. The code gets published in 1986. Almost 20 years later, in 2005, the law is passed that makes its release possible. And then, it's not until 2013 that it finally gets uploaded to the Internet Archive. That's a 27-year journey, from a physical paper document to being available to the entire globe.
And what about this crazy string of letters and numbers? This is not your average web address. It's called an ARC identifier. The easiest way to think about it is as a permanent, unbreakable address for this digital file. So years from now, when all our other links and bookmarks are broken, this one is designed to still work, to still point you right to this document. It's the technical stuff that makes building a library for the future actually possible.
The commitment to access goes even deeper. It's not just a single PDF you can download. You can grab it as an EPUB for your Kindle, as a full text file so you can search the whole thing, and get this, even as a DAISY file, which is specifically designed for people with print disabilities. This is what true, inclusive access really looks like.
Okay, let's bring this all home. We spent all this time talking about a pretty niche safety code for blasting. So why does the story of this one document matter so much to all of us, really? It matters because it represents a huge shift in how we think about information. In the past, this kind of vital public safety knowledge was often really hard to find, maybe buried in a library somewhere, or worse, locked behind an expensive paywall. But now it's liberated. It's available to any engineer, any student, any curious person with an internet connection. That's empowering.
You know, tucked away in the document's metadata online, you can find this quote from India's first Prime Minister, Jawaharlal Nehru. "Step out from the old to the new." It's just the perfect summary for this whole story, moving from an old world of closed-off information to a new one of open knowledge for everyone.
And hey, if you're wondering if anyone actually cares about a safety code for blasting from 1986, the answer is a big yes. As of right now, this one file has been viewed almost 5,000 times. That's nearly 5,000 moments where someone needed this specific information and was able to get it instantly for free. It shows that public access meets a real, tangible demand. So, in the end, what we've been looking at isn't just a file on a server. It's really an act of public service. Every single document like this that gets digitized and shared online is like laying another brick in a giant global library, helping to build a safer, smarter, and just a better informed world for all of us.
And that really leaves us with one last question to chew on. The story of IS 4081 is a story of liberation. And it just makes you wonder, what important knowledge in your own job, your own community, or your own country is still locked away, just waiting for someone to help it make that journey into the light?
You know, when you think of rock blasting, what comes to mind? Probably this huge, chaotic explosion, right? But what if I told you that what you're really seeing is science, a super controlled process that's all about reshaping the Earth with incredible precision? So yeah, let's get into it. I mean, just think for a second about the world around us. We've got tunnels, massive mines, entire highways carved straight through solid rock. How in the world do we do that? What does it really take to, move a mountain, one chunk at a time? Well, I'll tell you one thing. It's not about just finding the biggest bomb and lighting the fuse. Uncontrolled force, that's just messy. It's destructive, it's useless. If you actually want to build something, you need to be a lot smarter about it. The truth is, modern rock blasting, it's like a symphony. Seriously, it's this incredible performance where every single note, every calculation, every chemical mixture, every tiny millisecond of delay is all planned out to create a perfect, predictable result. Okay, so why do we even need to do this? Why do we need this powerful science? Well, it turns out our entire modern world is, quite literally, built on our ability to break up and move rock. I mean, rock blasting is the engine that drives so many industries. It's how we get the minerals for our phones and computers. It's how we clear the way for roads, for buildings, for giant dams. And it's how we dig out tunnels for subways and power plants. Without it, our modern infrastructure would literally hit a wall. Now, here's the thing. The success or failure of a blast, that's decided way, way before any explosives even show up on site. It all starts with a blueprint, a super detailed, meticulous plan that has to account for dozens and dozens of variables. And the complexity here is just, wow. Engineers aren't just, blowing stuff up. They're analyzing everything. Like, what kind of rock are we dealing with? How's it going to break? How do we control the vibrations so we don't shake up the town next door? They even have to plan for what they call fragmentation, basically how big the broken pieces of rock will be so the trucks can actually haul it all away. And yeah, this is definitely not a one-person show. It takes an entire team of specialists. You've got geotechnical engineers checking the rock stability, explosives engineers designing the perfect charge, and environmental engineers making sure the impact on the area is as small as possible. It's a real meeting of the minds. All right, so once that plan is locked in, the physical work can finally begin. But, surprise, it doesn't start with the explosives. Nope. It starts with a drill. They've got to create these super precise pathways to channel all that power. And this is a step where you absolutely cannot mess up. Precision is everything. These specialized drill rigs create a pattern of holes, they're called boreholes, deep into the rock. The depth, the diameter, the spacing, it all has to be perfect. Because that is what's going to dictate exactly how the energy is released and how the rock breaks apart. Okay, the pathways are drilled. Now it's time to load them up. But get that classic cartoon image of sticks of dynamite out of your head. We're talking about really sophisticated engineered explosives delivered by some seriously massive custom-built machines. Yeah, this picture gives you a great sense of the scale we're talking about. These trucks, they're basically mobile chemical plants. And the keyword here is safety. See, they carry the ingredients separately and only mix them into an actual explosive as they're pumping it into the borehole. This is a huge deal. It dramatically cuts down the risk compared to driving around with live explosives. And each of these trucks has a very specific job. Let's say it's a dry day, perfect conditions. An auger truck might mix a pretty simple, cheap agent called ANFO. But what if the hole's full of water? Then you've got a problem, right? Well, that's where the pump truck comes in. It delivers this water-resistant gel, an emulsion, that literally pushes the water out of the way. This is critical because you need the explosive touching the rock to get the most bang for your buck. Okay, so the explosives are in the ground. Now for maybe the most critical part of all. Telling each and every one of those boreholes exactly when to fire down to the millisecond. This is what's called the initiation system. Think of it like the nervous system of the hole blast. And the key to that whole system is this little device, the detonator. It's the trigger. It's a small but powerful charge that gets the main explosion going. But the real magic, it's the timing. These detonators can be made to go off instantly, or they can have these precise, built-in time delays. I know, they don't look like much, but these little things are the brains of the whole operation. And something that's super important is that a lot of modern systems are non-electric. They use what's called a shock tube. That skinny tube you see there, it sends the signal with a tiny chemical reaction instead of a wire. Now, why does that matter so much? Because it means they can't be set off by accident by stray electricity, like from a random lightning strike. That's a massive, massive improvement for safety. So no matter how complex it gets, every one of these systems really has three basic parts. First, you've got the blasting machine, which gives that initial spark. Second, you have the network of tubes or cords that carries that signal all over the site. And third, you've got the detonator down in the hole, which gets the signal and kicks off the main charge. And this diagram right here, this is where it all comes together. This is the magic. By using detonators with different delay times and hooking them up in just the right order, the engineers can control the blast with pinpoint precision. It's not one giant explosion happening all at once. It unfolds like a wave, with each row firing just a few milliseconds after the one before it. This lets them steer the energy, control exactly how the rock breaks and where it falls, and it keeps the ground vibrations to a minimum. See, it's not one big bang. It's 1,000 tiny, perfectly timed ones. It's that symphony we were talking about. Now, obviously, when you're dealing with this much raw power, safety has to be priority number one, and it is. Every single step, from how you move this stuff, to how you store it, to how you use it, is covered by super strict federal regulations. And just to give you a sense of the scale here, federal rules say that a single storage unit, they call it a magazine, can hold up to 300,000 pounds of explosives. Let that sink in. 300,000 pounds. That is a staggering amount of energy, and keeping it safe is an enormous responsibility. A big part of that safety is just physically isolating the explosives. The regulations require these magazines to be protected by barricades. This could be something natural, like a big hill or a thick patch of trees, or it could be a man-made wall of earth that's at least 3 feet thick. The whole idea is to have something there to absorb and deflect the force if anything ever went wrong. But you know, at the end of the day, it all comes down to this one really powerful idea from the blaster training manuals. An initiator can't tell the difference between energy you want it to get and energy it gets by accident. It's just going to do its job. And that's why every single procedure is built around control, meticulous care, and a deep, deep respect for the power you're working with. So the next time you're driving through a tunnel cut into a mountain or you pass by a giant quarry, you'll know that wasn't just chaos. That was a symphony of science. And it kind of makes you wonder, right? What other things that we see as just simple brute force are actually incredible marvels of hidden engineering and precision?